Hello everyone, welcome to Compiler Design video series. In our previous video, I have already discussed about unit number 8, code generation. In this unit, I have discussed different topics like issues in the design of code generator, runtime storage management, basic blocks and flow graphs, next use information, register allocation and assignment, DAG representation of basic blocks, peephole optimization, which we already discussed in our unit number 7, code optimization, how to generate code from DAG. These all topics are discussed in unit number 8, code generation. In today's lecture, I will discuss about unit number 3, parsing theory. In parsing theory, first, what is the role of parser? Then what is the difference between syntax tree and parse tree? What is the derivation, leftmost derivation, rightmost derivation? What is ambiguity? What is ambiguous grammar? Left recursion, left factoring, how to remove left recursion, how to remove left factoring. All these topics are discussed in this video. So let's start unit number 3, parsing theory. First, what is the role of parser? We have already discussed how to connect all phases of compiler. Your source program is passed to the lexical analyzer. Lexical analyzer generates the token, which gives token to the parser. Parser generate parse tree, then parse tree pass to the rest of phases of compiler. So whenever lexical analyzer generate the token, it gives to parser, then parser sends get next token to the lexical analyzer. All these phases of compiler are connected with symbol table. We expect that the parser is to report any syntax error. So it should also recover from commonly occurring errors. The methods commonly used for parsing are classified as top-down parsing or bottom-up parsing. In top-down parsing, builds the parse tree from top to bottom, means root to leaf, while in bottom-up parsing, it starts from bottom to top, means leaves to root. So in both cases, the input to the parser is scanned from left to right and only one symbol at a time. So we assume that the output of parser is some representation of the parse tree for the stream of tokens produced by the lexical analyzer. Then what is the difference between parse tree and syntax tree? Interior nodes are non-terminals and leaves are terminals, while in syntax tree, interior nodes are operators, leaves are operands. Parse tree are rarely constructed as a data structure, while syntax tree representing a program in a tree structure usually used syntax tree. Parse tree represents the concrete syntax of a program, while syntax tree represents the abstract syntax of a program. Now let's see with the example what is parse tree and what is syntax tree. Consider grammar like E gives E plus E, E gives E star E, E gives ID. Here consider this grammar, or grammar can be written like this: E gives E plus E, or E star E, or ID. Then your input string is A plus B into C. It means ID plus ID into ID. So how parse tree and syntax tree can be represented for this given input string? So your syntax tree would be ID plus ID into ID. Here over plus and star, the priority of star is higher than plus. So first draw ID into ID. Result of ID into ID is add with this ID. So here this ID represent your A, this ID represent your B, and this ID represent your C. In parse tree, start with grammar production. According to your input string, you have to choose grammar. Here first I choose E gives E plus E. E gives E plus E. Then after E gives E star E. Your E gives ID. So E gives ID, E gives ID, and E gives ID. So now you can find ID plus ID into ID. So this is your parse tree and this is your syntax tree. So there are different types of derivation. Mainly two types of derivation: leftmost derivation and rightmost derivation. So consider the grammar for different production, like S gives S plus S, or S gives S minus S, or S gives S star S, or S gives S divide S, or S gives opening bracket S closing bracket, or S gives A. Then what is leftmost derivation and what is rightmost derivation? Or differentiate rightmost derivation and leftmost derivation, or leftmost derivation versus rightmost derivation. So in your leftmost derivation, derivation of any string W in a grammar G is a leftmost derivation if at every step the leftmost non-terminal is replaced. While in rightmost derivation, a derivation of a string W in a grammar G is a rightmost derivation if at every step the rightmost terminal is replaced. So here consider the string A star A minus A. So S gives S minus S. Then this leftmost derivation, first remove leftmost non-terminal. So this S gives S star S. According to your input string, you have to choose production from the grammar. First, for leftmost derivation, I choose it from right hand side. s minus s. Then after remove this leftmost s, s gives s star s. Production of s is also a. So from here I can use a into a minus a, which I required. So s gives s star s, then minus s as it is. Now s gives a. So first remove leftmost s. So here I removed this s. S gives a. So I write a into s minus s. Then after removed next s. So s gives a. So a into a minus s. Now remove this s. A star a minus a, which we required. For rightmost derivation, consider a string a minus a, divide a. First s gives s minus s, then s minus this s derived s divided s. Now start it from right hand side. This s gives a. So s minus s divided by a. Now remove this non-terminal. So s minus a divided a. Now this non-terminal, because s produce a. So a minus a divide a. So equivalent leftmost derivation tree and equivalent rightmost derivation tree for this input string. Here leftmost derivation tree, s gives s minus s, then s gives s star s. So this s gives s star s, then after s gives a, s gives a and s gives a, and we derived a star a minus a, which we required. For in rightmost derivation tree, s gives s minus s. This s gives s divided s. So s gives s divided s. S gives a, s gives a, s gives a. So a minus a divide a, which we required. Next is ambiguity. Then what is ambiguity? What is ambiguous grammar? So any grammar is said to be an ambiguous if there exists more than one leftmost derivation or more than one rightmost derivation or more than one parse tree for given input string. If the grammar is not ambiguous, then it is called unambiguous. So an ambiguous grammar is one that produces more than one leftmost or more than one rightmost or more than one parse tree for the same sentence. So prove that the given grammar is ambiguous. So you have to prove that for input string you can generate more than one parse tree. So according to that you can say that given grammar is ambiguous. Here input is s gives s plus s or s minus s or s star s or s divide s or opening bracket s closing bracket or a, and your input string is a plus a plus a. For this input string you have to prove that given grammar is ambiguous. So first you prove that for a plus a plus a, you can generate more than one parse tree for given this string. Here s gives s plus s. For leftmost, here s gives a and plus s. S gives again s plus s. So a plus s plus s. Here s gives a. So a plus s, and this s gives a. So it's a plus a plus a. This type of arrow marks you don't write in your exam. So according to this, draw tree. S gives s plus s. S gives s plus s. Next s gives a. S gives a. From this s also product s plus s. S gives s plus s. Then s gives a and s gives a. So this is one parse tree for this input string. Now s gives s plus s. S gives s plus s. Now this s gives a and this s gives s plus s. So again s plus s plus s. Then s gives a, s gives a and s gives a. So your input is a plus a plus a. From this input string a plus a plus a. So here you can draw more than one parse tree for the given input string. So this grammar is ambiguous. This is another example that grammar is ambiguous. Your grammar is s gives a or sa or bss or ssb or sbs, and your input string is baab. First s gives bass. You can choose any of the production from grammar according to your input string. So here I choose s gives bss. Next choose b gives s gives a. So next is BAS. This as remaining as it is. This as gives A. Now from this as product like SSB. So S gives SSB. Now this S gives A. Then remaining is as it is. From this step S produce A. So your input string BAAAB, which we derived BAAAB. Now using another production, S gives SSB. Then remove this S derived from this S. Product is BSS. So BSS, this SB is as it is. Now from this product S gives A. So BA, these two S as it is and this B as it is. So BA SSB. Now also this S produce A. So next BAA, this one is as it is SB. Now also this S produce A, so your string is B A B, which is your given string. So from according to grammar and input string, you can derive more than one solution. So given grammar is ambiguous grammar. So how can ambiguity be reduced? So methods to remove ambiguities are by fixing the grammar, by adding grouping rules, by using semantics and choosing the parse that makes the most sense, by adding the precedence rules or other context sensitive parsing rules. So according to these methods, you can remove ambiguity in your grammar. Now algorithm for eliminate left recursion and left factoring. So first, what is left recursion, what is left factoring, and why we eliminate left recursion or factoring? Because in top-down parsing, left recursion and left factoring will not work. So first you have to eliminate either recursion or factoring available in your grammar. So grammar is said to be left recursive if it has a non-terminal A such that there is a derivation A gives A alpha for some string alpha. It means you have any production which produce same product in your right hand side. Here production from A, in right hand side it's also a. So A gives A alpha for some string alpha. So in top down parsing methods cannot handle left recursive grammar. So a transformation that eliminates the left recursion is needed. So this is the algorithm how to remove your left recursion. Your input grammar is G, then you can find equivalent left recursive grammar. So first assign an ordering A1, A2, A3 up to AN to the non-terminals of the grammar. For I equal to 1 to n, then for j equal to 1 to I minus 1, then replace each production of the form AI to AI y by the production AI to delta 1 gamma or delta 2 gamma or delta k gamma, where AJ gives delta 1, delta 2 up to delta k are all the current AJ productions. Then eliminate the intermediate left recursion among the AI production. So here basic rules for removing the left recursion. If you have any grammar in this form, A gives A alpha or beta, then you can write into this form which is removed left recursion. First A gives beta A dash production of given terminal, non-terminal. A gives beta A dash and A dash gives alpha A dash or epsilon. Let's see with example. Consider the following grammar like E gives E plus T or T, T gives T star F or F, F gives opening bracket E closing bracket or ID. if there is any left recursion in given grammar, then first you have to eliminate that recursion. In this grammar, there are two left recursive production, like E gives E plus T or T and T gives T star F or F. In both this production, left hand side and right hand side, both non-terminals are same. So you have to remove left recursion from these two grammar. So eliminate immediate left recursion from above grammar. Then we obtained E gives, here compare this grammar into this one. E gives E plus T or T. So here this E is your A. Gives A, it means this E. Alpha is your plus T, or this or this or. So beta is your this T. So compare to this, then convert into A gives beta A dash gives alpha A dash or epsilon. So for this grammar, E gives T E dash beta A dash. So this one is your beta, and A dash, here non-terminal is A, so A dash, here non-terminal is E, so E dash. So your first statement is E gives T E dash. Next, A dash gives, so E dash gives alpha. In this case, alpha is plus T, so plus T A dash, so here E dash or epsilon. So remove left recursion from this line. E gives E plus T or T. After recursion, it becomes E gives T E dash. E dash gives plus T E dash or epsilon. Then remove from this line. T gives T star F or F. Again compare this with A gives A alpha or beta. Here your A is T. This T. Then your alpha is star F and your beta is F. So A gives beta A dash. So T gives F T dash. Next, A dash gives, T dash gives star F T dash or epsilon. So T gives T star F or F. After left recursion, T gives F T dash. T dash gives star F T dash or epsilon. Next is F gives opening bracket E closing bracket or ID. Here production from F. Right hand side immediate, there is no any F. So there is no any left recursion. So write down this product as it is. So F gives opening bracket E closing bracket or ID. So finally after the left recursion, your grammar will be E gives T E dash, E dash gives plus T E dash or epsilon, T gives F T dash, T dash gives star F T dash or epsilon, F gives opening bracket E closing bracket or ID. Next is left factoring. So left factoring is a grammar transformation that is useful for product producing grammar suitable for predictive parsing. So you have more than one product produced from right hand side with same terminal, then it is also eliminate. So algorithm for left factoring, your input is grammar G and output is equivalent left factored grammar. For each non-terminal A, find the longest prefix alpha common to two or more of its alternatives. If alpha is not equal to E, for example, there is a non-trivial common prefix, replace all the A productions. For example, A gives alpha beta 1 or alpha beta 2 or alpha beta 3 up to alpha beta n or gamma, where gamma represents all alternatives that don't begin with alpha. By A gives alpha A dash or gamma and A dash gives A gives alpha A dash or gamma and A dash gives beta 1, beta 2 or beta n. So here A dash is a new non-terminal. Repeatedly apply this transformation until no two alternatives for a non-terminal have a common prefix. It means if in production of any non-terminal you have more than one common prefix, then you can convert that prefix into this manner, like A gives alpha beta 1 or alpha beta 2 up to alpha beta n or gamma. So here these all products common prefix will be alpha. So A gives alpha A dash or here gamma, which have no any common prefix like alpha. So A gives alpha A dash or gamma and A dash produce beta 1 or beta 2 up to Bn. In general, if A gives alpha beta 1 or alpha beta 2, then A gives alpha A dash and A dash gives beta 1 or beta 2. Let's see with the help of example. Here A gives x, b, y, a, then x, b, y, a, z, a or a, and b gives a. In this grammar, left factoring is common production from right hand side. Here A produce three different production. In these three production, from two production, this one is common, x, b, y, a, here x, b, y, a. So it's become your alpha. So convert it according to this formula. A gives alpha beta 1 or alpha beta 2. A gives alpha A dash and A dash gives beta 1 or beta 2. So here A gives x, b, y, a. X, b, y, a. This is your alpha. So remaining is alpha A dash. So A gives x, b, y, a dash. This is your not common prefix product. So it is as it is, or A. And this A dash gives beta 1 or beta 2. So A dash gives Here this is alpha, so this is your beta. ZA, so ZA, from this there is no any product, it means epsilon. So write ADS gives ZA or epsilon. In this product B gives B, there is no any left factoring, so no need to remove factoring. So write as it is, B gives B. So your grammar, A gives XBYA or XBY A ZA or A, and B gives B. So after left factoring, the grammar becomes A gives XBY A dash or A dash gives ZA or epsilon, and B gives B. So this is your left factoring. In your GTU exam, questions will be asked like, what is parser? Explain the role of parser. Differentiate leftmost derivation and rightmost derivation. What is ambiguous grammar or what is ambiguity? Show with the help of example or check whether the given grammar is ambiguous or not. Write an algorithm for eliminate left factoring. Write an algorithm for eliminate left recursion or remove left factoring or left recursion from given grammar. So this type of questions are asked in your GTU exam. Thank you.